Alright, we're going to try this again. I believe this just should be going through now. Alright, it looks good. Okay, I'm just going to trust that this is going through and hope it is. It looks like it is. So we will continue, or start. Alright, so hello everyone. Welcome back to the mathematics library. Today we're going to be looking at our third graph algorithm. It'll be the Ford-Fulkerson algorithm, which is it's an algorithm that will allow us to determine the maximum flow of a graph. And what do I mean by flow? Well, if we consider a weighted graph using the weights as capacities, so for example, let me just turn this down a tad. All right. So if we consider, let's say we have this weighted graph here, and we want to consider the weights of each edges as a capacity. So, for example, the maximum flow that an edge can take. So, for example, the maximum flow that you could send from 0 to 1 is 11 units of flow. Now that can be something like units of cargo. So we could send 11,000 tons of cargo along this path here. So this will, you would obviously see here, all right, there's an advantage to figuring out the maximum flow of a graph and what that maximum flow contains. So if we wanted to find the maximum flow going from 0 to 5, we would have to consider all of our paths here, and then that'd be, and then we could figure out the maximum number of units of flow that we could send from 0 to 5 based on the weights of the capacities, the maximum capacities of each edge. So the idea is we are going to continue to find different paths from the source. So we have our source node, and we want to go to our destination node over here. So let's see what paths we have. So we'll do them in a big brown. So we have this path, like so. We have this path. Or let me do these in different colors, actually. We have this path. We have this path. And then we also have this path. So there are three possible paths that we can see to go from our source, which is 0, to our destination, which is 5. And depending on how much flow we want to send on each path, we will figure out a way to find the configuration that sends the maximum amount of flow along these paths. So once again, the idea is we're going to continue to find our paths and then increment the minimum flow, or what's called the bottleneck, increment that to the maximum flow. So for example, if we look at this path here, the bottleneck would be the smallest value, or 1, because it is kind of the maximum limit for the amount of flow that you can send on this path. So here we have, if we wanted to send along the path 0, 2, 1, 3, 5, we could only send one. We can only send a maximum of 1 unit of flow along this path, because if we sent 12, for example, from 0 to 2, we could do that. But then where's the 12 going to go? You can only send one of those units from 2 to 1. So that's how that would work. Now when we configure this, look at this, 1 plus 11, this is going to equal 12, so maybe we can distribute this flow into 2 different paths, and maybe that could work out. So yeah, we're gonna look at the algorithm called the Ford-Fulkerson algorithm, which will find this. So the Ford-Fulkerson algorithm uses a method that involves the residual graph. So the residual graph is essentially it stores what we have done and what we can undo. So for example, if we consider if we just do a path, and let's say we wanted to do the path 0 to 4, so I'll just do this 0 to 4 3 5, and let's say that we sent 6 units of flow. So we would do 6 out of 12 here, 6 out of 11 here, 6 out of 7 from 4 to 3, and then 6 out of 19 from 3 to 5. And that's just, I'm just using the 6, this is the slash, will denote the present amount of flow slash maximum flow. So we can kind of think about, all right, what are the remaining capacities? So if we were to kind of look at the remaining capacities in another graph, it would be, we would go 0, 1, 2, 3, 4, 5. So from 0 to 1, we haven't touched the flow. So that's going to go, it's still going to have a remaining capacity of 11. 0 to 2, however, will have a remaining capacity of 6 because we have used 6 units of flow, but it has 6 units left. So we can still send 6 units along this path, the forward edge here. 2 to 4 will have 5 leftover units for the same reason, because if we have a maximum of 11 and we send 6, then we can only send 5 more. 2 to 1 untouched, so it's just the original as 1. 1 to 3, still 12. Now 4 to 3 has 1 leftover unit, since 7 is the maximum capacity and we send 6 units of flow, so that'll give us 1 extra unit. And then 3 to 5 will be, it will have 13 units left, and then 4 to 5 will still have 4. Now the part that makes this residual is when we consider the backwards edges, so stuff that we can kind of undo. So we're going to think about this as, all right, well, if we sent this much flow, what is the flow that we can undo? So if we consider the edges on the reverse side, we have 6 units here from 2 to 0, because we have sent 6 units from 0 to 2. So we kind of we can consider this as a way to undo that flow. So the backwards edge from 2 to 0 is 6. The backwards edge from 1 to 0 is 0. Because we have sent no units of flow along the edge 0 to 1, so we cannot undo anything. And then the backwards edge from 1 to 2 will be 0 as before. Then 4 to 2, the backwards edge here, will be 6, since we sent 6 units of flow along it, and we still have, so we can undo those 6 units. And then from 4 to 3, we can undo 6 units again. Oops, wrong way. And then from 5 to 3, we can undo 6 units as well. And then the rest of the edges are untouched. So 0 and 0. So that's going to be this is going to be our residual edge, or our residual graph here, considering if we send 6 units of flow along the path 0, 2, 4, 3, 5. So the Ford-Fulkerson algorithm takes this and says, all right, well, let's only look at the residual graph, and let's always try to find a path from the source to the destination in the residual graph. And every time we add a forward edge or increase flow along a forward edge, we will decrease the remaining capacity on that forward edge, but increase the capacity on the backwards edge. Now the logic here is just like I said before. When we send flow along an edge, we want to decrease the remaining capacity since we're taking out more of the capacity, and then we want to increase the capacity that we can take back or undo. So like here, when we sent 6 units along from 2 to 4, we have 5 units left, which is the remaining capacity on the forward edge, but we can undo those 6 units that we sent, which is the capacity on the backwards edge. So Ford-Fulkerson will essentially use this residual graph, and we will find every path, even with the backwards edges, since we can undo flow, and every time there is a path in the residual graph from the source to the destination, we will augment that flow or the bottleneck of that path to each of the edges in the path. So let's look at this example here. So we have this as our original graph. And let me just start with the residual graph here of a graph without any flow at all. I'm also just going to copy and paste this so I can just have it. Alright, so this is our residual graph here. So the original flow is, right, I need to update the original flow, or set the original flows. So on the forward edges, it's all going to be the same. The remaining capacities will just be the weights since we have not sent any flow yet. So we do 12, 11, 1, 11, 12, 7, 19, 4. And all the backwards edges are just going to be 0. Because we cannot take back any flow since we have not sent any. So this is the original residual graph here. Now let's find a path from 0 to 5. So let's do 0, 1, 3, 5. So 0, 1, or 0, 1, 2, 4, 5. So this here. Or wait, no, this won't work. Sorry, that's not a path. Because in the residual graph, even though there is an edge from 1 to 2, which is the backwards edge, it has no weight, so we cannot send any flow. So the path has to be valid in the sense that there has to be a positive remaining capacity on each of the edges in the path. So a valid path would be 0, 1, 3, 5. Now the bottleneck is going to be the smallest weight, which is 11. Because that is 11, the minimum of 11, 12, and 19. So what we're going to do is we're going to add 11 units of flow to each of these edges. So what the result will be is, I'll just do the other edges, the unaffected edges right now. So 12, oops, 12, 0, 0, 1, 11, 0, 4, 0, 7, 0. So when we increment 11 units of flow, we are decreasing the remaining capacity of the forward edges by 11. So the edge from 0 to 1, we decrease its capacity by 11. So this becomes a 0. So there is no more capacity along the forward edge from 0 to 1. Now on the backwards edge, this increases to 11 because we can take back 11 units of flow. From 1 to 3, we have one leftover. We have one leftover unit of flow because it's 12 minus 11 is 1, and then we can take back 11 units of flow. And then 19 minus 11 is 8, and we can take back 11 units of flow. Notice how the sums of these weights will always add back to the original weight of the edge. So 11 plus 0, 11 plus 1, they will always sum back up to the original weight. All right, now let's find another path. Let's do 0 to 2. 2 to 1, 1 to 3, and 3 to 5. Here, the bottleneck is 1. That's the smallest weight of 12, 1, 1, and 8. So once again, I'll draw in the unaffected edges first. Right, and then for the affected edges, since we send 1 unit of flow from 0 to 2, the remaining capacity is 11, and we can take back 1 on the backwards edge. This becomes a 0. We can send no more units and then take back 1. We can send no more units from 1 to 3 and take back 12. Or this should be 12 here. And then 3 to 5, we can send 7 more units but take back 12. All right, let's do one more path. Let's get a 0 to 2, 2 to 4, 4 to 3, 3 to 5. Here the bottleneck is 7. 7, 7, 11, 11. Once again, we have the unaffected edges, 0, 11, 1, 0, 12, 0, 4, 0. And then we're setting 7 units of flow, so we have 4 left over from 0 to 2, and we can take back 8. 2 to 4, we have 4 leftover units and can take back 7. Then 4 to 3, we have 0 leftover units, can take back 7. And then 3 to 5, we have 0 leftover units and can take back 19. Once again, these two will always sum back up to the original weight. All right, there should be one more path, I believe. Yeah, it's just 0, 2, 2, 4, 4, 5. Here the bottleneck is 4, which is the weight of all, which is the remaining capacity of all 3 forward edges. So I'll draw in the unaffected edges, 0, 12, 7, 0, 0, 19, and then the 4. So if we send 4 units from 0 to 2, we have 0 left over, and we can take back 12. From 2 to 4, we have 0 left over, can take back 7, or can take back 11, and then from 4 to 5, we can send 0 more and take back 4. And there are no more possible edges or no more possible paths from the source to the destination. And I know that because the only 2 edges going into 5 have a 0 remaining capacity. So there's no way to get to it. And also all the outward edges of 0 have a 0 capacity. So let's look at this. Let's look at this graph here. For some reason, it seems that this example is kind of crappy, where the maximum flow is just the flow of each edge, so this example sucks. However, it still is representative because the maximum flow is just the original graph. We can send the maximum capacity along each edge to get the maximum flow, which is, in this case, I guess, cool, but it's a shitty example. So the maximum flow here will just be 23. How did I get that? Well, I mean, you can look at 0 at the source node, and how much flow is the source node sending out? Well, we can tell that by the remaining capacity on the forward edges, which is 0 and 0. And we can also, or not by that, but we can sum up the remaining or the capacities on the backwards edges. So 12 plus 11, which is equal to 12 plus 11. But you also might recognize this as the sum of the bottlenecks. I mean, and you can also think about that. Okay, that makes sense because the bottlenecks are the maximum amount of flow that we send on each path. So if we increment the maximum flow by the bottleneck every time, we will get the maximum flow. So this is equal to 11 plus 1 plus 7 plus 4. Equal to 11 plus 1 plus 7. Let me do this in the orange. 11 plus 1 plus 7 plus 4. So the sum of the bottlenecks. So yeah, that is the Ford-Fulkerson example. It's, once again, a shitty example. It won't always work out. I mean, I don't think it'll always work out like that. Because this graph was pretty simple. But I also think, yeah. But yeah, it seems like a much more complicated problem, but when we do it like that, it kind of seems to make sense. Because every time we can find a path with remaining capacity from the source to the destination, then we will just increase the capacity or increase the flow by the bottleneck of that path, which makes sense. And every time there is a path, we can augment some bottleneck. So yeah, that's cool. All right, so we will get into writing this code now. All right, so let's first hop over into Visual Studio Code, and we'll go into graph.h, the header file. We need to write a few signatures. First one is going to be, we're going to have a new DFS method. And this one, so the DFS method that we have already is just a general DFS. This will create a forest that we this will create a forest a forest of nodes in that we can just find through all the sources. So in this one, we're gonna have, it's gonna return an integer, which will be the bottleneck, and we're gonna call it path DFS. So the path DFS will be a targeted search. We're going to want to find a path from a specific source to a specific destination. So what we're going to do here is we're going to pass in a graph pointer G, an integer source, an integer destination, a character pointer for visited. So we're going to forget the times, the discovery time, the finishing time, and we're just going to have a visited array. And then we will also have an integer for an integer array for the predecessor array, which is what we have all the time. And then we'll have a method to start this. So integer graph path DFS start, and this will take in a graph pointer G, an integer source, an integer destination, and an integer array for the pointer or for the predecessor array. All right, let's copy and paste these over. New graph.c. And we'll start with path DFS start. All right, so all we're going to do here is we're just going to construct the visited array. So we're going to say character pointer visited is equal to malloc g.n times the size of a character. Or can we do Boolean, since we have the... If we include cmathematics.h in here, we can use we can do a Boolean here. Yeah. So g.n times the size of a Boolean, where the Boolean is just a type def that we have in the common header file. You can also just use character, it doesn't make a difference. All right, so then we're going to go through each node. So for integer I is equal to 0, I is less than g.n, I plus plus. Then visited at I is equal to 0, and predecessor at I is equal to -1. Or we can say visited at I is equal to false. And then what we're going to do is we're just going to call the DFS using this new the allocated arrays. So return graph path DFS in graph G from the source to the destination with the visited array visited and the predecessor array P. So we're going to have a double return here. One, the integer return will be the bottleneck of the path, and then the second return will be just the output to the predecessor array. All right, now for the actual DFS, it's going to be very similar to what we have already, except it's going to be a little, except we're going to have a special conditions to target this. So we're first going to say if not visited at source. So if the source has not been visited yet, then we're going to first mark the source as visited. So visited at source is equal to true. And then dynamic, we're going to iterate through the, or sorry, not yet. Then we're going to say if g.adjacency mode, and then we're going to iterate through the edges, as with the earlier DFS. So edge pointer e is equal to null. Then dynamic array iterator, it is equal to dynamic array iterator new g.adjacency lists plus source. So we're going to the source's list of edges, and then while e is equal to dynamic array iterator next, using a reference to it. So while this returns a value, then we're going to determine if there's an edge. So if e.wait and not visited at e.v2. So this condition here is if the edge has wait and the second vertex in the edge has not been visited. So this condition here, if e.wait, is key, because if you remember, we cannot send any more flow along an edge that has a 0 capacity. So we need to make sure that the wait is not 0. I made that mistake earlier, but it was good. It was good for demonstration. Maybe I should make more errors like that, but yeah. So this has a 0 weighted edge, so we cannot send any more flow. So we're gonna say that there's no edge, or we're gonna consider it like there's no edge. So edge from source to I or to e.v2 has wait. e.v2 not discovered. And then we're going to determine if we found the goal. So if e.v2 is equal to the destination, then we found the goal. So we're going to set the predecessor. So p at dst is equal to the source. Visited at dst is equal to true. And then return e.wait. Oh wait, I forgot to do something in path DFS start. We have to get the result of path DFS as a return variable and then free the visited array. So free visited, and then we can return rect. Yeah, I just forgot to do that. So this, we need to free the array once we're done with it. All right, so here, if the second vertex in the edge is the destination, then we have found the goal. So the predecessor of the destination will be the source, which is where we're starting the DFS from, this iteration of the DFS from. And then we set the destination to visited, although this doesn't, we can actually just remove this because it doesn't matter. And then we return the wait. Now, why did we return the wait? Well, if we want to return the bottleneck and we found a single edge on the path so far, the bottleneck of a single path, of a single edge path, will just be the weight of that path, or the remaining capacity of that path, because there's no other edges to have a smaller remaining capacity. Now, else, we're going to recurse down. So recurse along edge. So integer weight is equal to graph path DFS, so we're recursing down. In graph G, the source will now be e.v2, as with in the regular DFS, where when we recurse, we go into the second vertex of the edge. So e.v2, then the destination is still the destination, visited is still visited, and the predecessor array is still p. So we get the weight here. Now if weight, then found a path to the destination. So we're gonna set the predecessor since we have found a path. So predecessor of e.v2 is equal to the source, and then we're going to return the smaller weight. So return e.weight is less than weight, question mark. We're using ternary operators. So question mark, if it is less than, we want to return the weight of the edge since we have found a smaller weighted edge. Otherwise, return the weight. So this is just a comparison. Return the minimum of e.weight and weight, essentially. And otherwise, we don't have to do anything. We don't have to set any predecessors because we didn't find a path there. All right, so this is for the adjacency lists. Now, if it's an adjacency matrix, so else here, else in the highest level if statement or the second level if statement, we're going to iterate through the neighbors. So for integer I is equal to 0, I is less than g dot n, I plus plus, then if g dot adjacency matrix from source to I and not visited at I, so we're essentially having the same conditions here. So if the edge has weight and the second vertex is not visited, then we want to do the same condition. So if I is equal to dst, then we've found the goal. So set the predecessor, so p at dst is equal to the source, visited, or we don't need to do that, and then we can just return the weight of this edge. So return g.adjacency matrix from the source to I. Now otherwise, we're going to recurse along the edge. So integer weight is equal to graph path DFS in graph G from the source I now, since we're going to the ith neighbor, or the ith node is the neighbor. The destination is still the destination, visited array is still visited, and the predecessor array is still the predecessor array. And then once again, if the weight, then we have found a path to the destination. So we're going to set the predecessor, so p at I is equal to the source. Notice how we're just replacing e.v2 with I, and then we're going to return the smaller weight. And here the smaller weight, or the weight of this edge, will just be the value in the adjacency matrix. So return g.adjacency matrix from the source to I is less than weight, question mark, g.adjacency matrix from source to I, otherwise weight. So this is just the minimum. And then after everything, we're just going to return 0 as our base case when we have found no path. So if none of these conditions pass, then we're just going to go to this return statement here, meaning that we did not find a path, so there is no bottleneck of a non-existent path. All right, so that's the path DFS. You can test that out if you want, but I'm just going to skip that because I know it works. I'm just that good. I probably fucked this up, but we will see later on. However, this does look good to me. So once again, path DFS is a targeted DFS starting at a specific source and looking for a specific destination, and it returns the bottleneck. All right, let's head back into graph.h, and we're going to have our signature for the Ford-Fulkerson algorithm. So Ford-Fulkerson algorithm will return another graph. So return a graph structure because we want to see what the graph of containing the maximum flow is. So for example, in this one, the return would just be the original graph because we just sent the maximum flow along each edge. So it would just be, we're just going to have those we're just going to return the weights of each edges, or we're going to return the graph where the weights of each edge represents the flow, not the remaining capacity anymore. We input a graph with weights representing the remaining capacity, and we're outputting a graph with the weights as the flow along those edges, which attains the maximum flow. So returns a graph. We're going to call this graph Ford-Fulkerson. Take in a graph pointer G. Take in an integer source to an integer destination, and we're going to output the maximum flow to an integer pointer, max flow ret. So once again, a double output function. All right, so let's copy the signature over. Hold on, let me figure something out. Let me look at something real quick. Oh, we do have a minimum macro. So over in path DFS, instead of doing a stupid ternary operator, we can just return the min of g.adjacency matrix at from source to I and weight. Oops. And then the same thing above. Just like that. So that just looks a lot cleaner, in my opinion. Alright, as for Ford-Fulkerson, let's go ahead and get started. So the first thing we're going to do is we're going to create two copies of the graph. So the first one will be the return graph, and the second one will be the residual graph. So we're going to have a graph ret is equal to graph copy G, and then graph residual is equal to the graph copy of G as well. Oh, does graph copy not exist? Oh, did we not write that? Oh, shit. Oh, we never did that. Oh, might be fucked. Uh-oh. Oh, we never did that. That's great. All right, perfect. All right, I guess we have to do that now. That's fine. All right. Hold the brakes. Put the brakes on. We're going to write our utility method, graph copy. So it's just going to be a, it's going to return a graph. It's going to be graph copy. Passing a graph pointer G. All right, and then we're just going to paste in the signature. Let me just look for my reference here. Here we go. Perfect. All right, so we're going to allocate a graph structure using an initializer list. So the pointer, the union pointer will be null. Adjacency mode will be g.adjacency mode, and we're pretty much just copying all the values over. So g.adjacency mode, g.n, g.number, or sorry, this could be wrong. We need n, a pointer, and adjacency mode. That's all right. So this is wrong. So it's just going to be g.n, a null pointer, and then g.adjacency mode. All right, I overcomplicated that. Perfect. So once again, this null pointer here just refers to this union here. All right, then we want to copy over the edges. So if g.adjacency mode, then it's going to be adjacency lists. So ret.adjacency lists is equal to malloc g.n times the size of a dynamic array. So this is going to be similar to the constructor, except we're just copying stuff over. And then we're going to iterate through each list. So for integer I is equal to 0, I is less than ret.n, I++. And then we're going to allocate each list. So for ret.adjacency lists at I is equal to dynamic array, allocate, and the size will be g.adjacency lists at I dot size. So we just want to allocate the sufficient memory so we don't need to resize it all. And then we're going to iterate through each edge and copy it over. So for integer j is equal to 0, j is less than g.adjacency lists at I.size j++. Then we're going to say we're going to get the edge. So edge pointer E is equal to g.adjacency lists at I.list at j. So get the jth edge in the ith list. And then we're going to say dynamic array add last ret.adjacency lists plus I. And we're going to create a weighted edge. And the v1 will be e.v1, e.v2, and then e.weight. So we're simply just calling the edge constructor for each of the edges and just copying the memory over. As for adjacency matrices, it's a little easier. So we're going to do else here, and then we're going to allocate the memory. So ret.adjacency matrix is equal to malloc g.n times the size of an integer pointer, because it's a double pointer, and then for integer I is equal to 0, I is less than g.n, I++. Then we're going to allocate each row of the array. So ret.adjacency matrix at I is equal to malloc g.n times the size of an integer. And then we're going to copy the memory over using memcopy. So memcopy, the destination is ret.adjacency matrix at I. The source is g.adjacency matrix at I. And the size will be g.n times the size of an integer, which is the size that we allocated right here. So we're simply just copying all the memory over from each row. All right, so we have a copy method now. I'm going to take half a second as a break. All right, let's head back to Ford-Fulkerson, the method here. So now that graph copy actually returns a copy of our graph, we can start writing this code here. So we're first going to have a placeholder for the maximum flow. So integer max flow is equal to 0. That just will be what it starts as. And then we'll increment with each path that we find. Now we're going to go into our main loop. So we're going to first allocate a predecessor array. So integer pointer p is equal to malloc g.n times the size of an integer, and then integer path flow. So the path flow is just going to be the return value of path DFS. So we're going to say while path flow is equal to graph path DFS start. We're going to start a DFS in graph in a reference to resid, since we're going in the residual graph. You know, this example also sucked because we never got to go backwards on an edge. Now, it could be possible to do that where, well, I don't know about this. I don't think it is on this graph, but we could do that actually. If we wanted to take away flow from one edge and give it to another edge, we could do that, which would work, and that's how this algorithm is designed to work. So we're going to do the path DFS on the residual graph, starting at the source, going to the destination, and the predecessor array is just p, and then 3 closing parentheses, or just closing parentheses. So while a path exists from the source to the destination, and once again, this is called the augmenting path. So since we have a predecessor array, it is easy to trace back to walk back through the path. And I talked a little bit about this with the Dijkstra algorithm, where when we return a predecessor array, it's kind of a tree in and of itself. Because if we look at the predecessor array, we can start at our destination, which may be 5, look at its parent. Okay, the parent is 2, so we go to 2. Parent of 2 is 3, so we go to 3. and then parent of 3 is 0, so we go to 0. So that's going to be the logic here. So we're going to do for integer I is equal to destination. I does not equal the source. I is equal to the predecessor of I. So what does this loop mean? So we start at the destination in the parent array, or in the predecessor array. So the index, once again, matches at 1-to-1 with the node numbers. So we start at the destination node, and we will do something in this loop. And then in the incremental step, we go to the predecessor of I using the array access, or using the array elements. And the predecessor of I is just the predecessor array at index I. And we want to go until we find the source as I. So we're going to say edge from P at I to I is in the augmenting path. So now we're going to deal with the edges, and we'll start with adjacency lists. So if g.adjacency mode. So we are first going to find the edge. Or find the forward edge in the path. So we're going to iterate. So edge pointer e is equal to null. Dynamic array iterator it is equal to dynamic array iterator new residual.adjacency lists plus the predecessor at I, because this is a forward edge. So the edge goes from the predecessor of I to I. So we want to get the list of edges originating from the predecessor of I. Now while e is equal to dynamic array iterator new, while this returns a value, or next actually. So while this returns a value, we're going to say if e.v2 is equal to I, then we're going to decrease the remaining capacity on the forward edge. So e.wait minus equals path flow, where path flow is the bottleneck. And this value is guaranteed to never go negative because the path flow has a maximum, or is bounded by the remaining capacities of each of the edges. So we can never subtract a larger value than this. And then we're going to break out of the loop here. Alright, so we don't need to check to see if this edge does or doesn't exist. We know it exists because it's a forward edge in the path. So we know that by going through the residuals adjacency list for the predecessor of I, we will find the edge, because that's how DFS works. Now we want to find the residual edge. So we're going to say Boolean residual found is equal to false. Then we're going to set e to null, and then we're going to reset the iterator. So it is equal to dynamic array iterator new residual.adjacency lists plus I this time. So we're finding the residual edge, which is the backwards edge. So it goes from I to the predecessor of I. So while e is equal to dynamic array iterator new, passing in a reference to it. So while that returns a value, we're going to say if e.v2 is equal to p at I. So if we found the edge with the predecessor, we're going to say residual found is equal to true. Then we're going to increment the weight of on this residual edge. So e.wait plus equals path flow. Now why do we add it? Well, once again, on the residual edges, we can kind of take away weight. Or on the residual edges, we want to use them to undo flow. So we're going to increment the remaining capacity, because when we put flow along the forward edge, we're increasing the amount of flow that we can take away or essentially send along the backwards edge. Those two statements are equivalent. And then we're going to break. Now if we don't find this, it is possible to not find an edge here because the residual edge may not exist yet on the residual graph. We're going to say if not residual found, then we're going to add an edge. So dynamic array, add the last. We're going to add to resid.adjacency lists plus I, and then the edge to add will be create weighted edge from I to the predecessor of I, and the weight will be the path flow. Because we can kind of consider this as if the edge does not exist yet, the remaining capacity on it is 0. So when we add, this will just be a 0 plus path flow, so we can just put the path flow as the weight. Alright, so that's that for the adjacency lists. Now for the adjacency matrix, it's actually super fucking simple. So else, we're going to say decrease weight by the path flow, so the remaining capacity. So residual.adjacency matrix from the predecessor of I to I minus equals path flow. Once again, this is guaranteed to never go negative. And then add weight to the residual edge. And this will just be residual.adjacency matrix from I to the predecessor of I plus equals path flow. And that's that. It's just those two lines for the adjacency matrix. It's super simple. Alright, and then outside of this for loop here, we're just going to add to the path flow. So max flow. Oh shit, what the fuck was that? Max flow plus equals path flow. So once again, same reasoning where when we find an augmenting path, we're just going to add the bottleneck to the maximum flow. And then outside of the while loop, we're going to say just free the predecessor array because we do not need the memory anymore. Okay. We simply cannot just say return route. Well, yeah, we simply just can't say that. The reason why is because we're still considering the weights of these edges as the remaining capacity, not the actual flow along the edge. So to convert from the remaining capacity to the flow attained on each edge, we need to do something. So we need to look at the original the original weight on the edge, and we're essentially going to subtract the remaining capacity. So the original capacity minus the remaining capacity will give us the flow that we sent along. So where's my pen? Here it is. So for example, right here. Oh, right here. The flow from 0 to 2 will be the original 12 minus 0, which is equal to 12. And that makes sense because we know that we can send 12 units of flow along this edge here. So that's how that works. Alright. So before returning, we have to subtract remaining capacities from original capacities to attain, or to get attained flow. So we're going to say for integer I is equal to 0, I is less than ret.n, I plus plus. We're just going to go through each node here, and then if ret.adjacency mode, and if so, we're going to do a list. So for integer j is equal to 0, j is less than ret.adjacency lists at I.size, j plus plus. So we're going to get both edges here. So edge pointer ret edge is equal to ret.adjacency lists at I.list at j, and then the same index access for the residual edge. So edge pointer resid edge is equal to ret or resid dot adjacency lists at I dot list at j. So we get the jth edge and the ith list, and then we're simply just going to subtract. So ret edge dot weight minus equals residual edge dot weight. And this guarantees that we don't look at any of the backwards edges, simply because in the original we're only iterating through the edges of the original graph right here, which is just the return, and we haven't touched the return graph the entire time. That's just been copied at the first line, and that was it. So ret edge dot weight minus equals residual edge dot weight. And then otherwise, we're going to do the matrix. So for integer j is equal to 0, j is less than ret.n, j++, then if ret.adjacency matrix from I to j, so if there's an edge in the original graph from I to j, then we're going to say ret.adjacency matrix from I to j minus equals resid.adjacency matrix from I to j. And I didn't say it for here, but we will not be looking at any of the any possible residual edges that we did not want to find, or that we added beyond. These edges will match up 1 to 1. So like each edge will have the same start and end point, just because these graphs, or the return and the residual graph, both started out as the same graph. So they will still have the same initial edges. So the jth edge in the ith list of the return graph will be the same edge, or the same will have the same start and end points as the jth edge in the ith list of the residual graph. So we're only adding beyond, we're only adding onto the residual graph the edges there. We're not touching the returned edges. All right. Now, with just a few steps before we return, we need to say if max flow ret. So if we want to return something to the null or to the pointer, then we're just going to dereference max flow ret and set it equal to max flow. And then we're going to free the residual graph. So graph free, pass in a reference to residual. And that's that. Alright, so that is Ford-Fulkerson. It's good shit. That was actually a lot quicker than I thought. Interesting. Alright, let's test this out with our example. Alright, so let's look at our. Alright, so we have 6 nodes here. Oh, what is that? Alright, so we have an edge from 0 to 1 with weight 11, from 0 to 2 with weight 12, from 1 to 3 with weight 12, oops, messed that up, from 2 to 1 with weight 1, from 2 to 4 with weight 11, from 3 to 5 with weight 19, from 4 to 3 with weight 7, and 4 to 5 with weight 4. Alright, so let's just run this just to make sure that we're getting the proper graph. Alright, so 0 to 1, 11, 0 to 2, 12, 1 to 3, 12, 2 to 1, 1, 2 to 4, 11, 3 to 5, 19, 4 to 3, 7, 4 to 5, 4. Perfect. Alright, now let's get our Ford-Fulkerson graph, or our maximum flow graph. So graph FF, graph, not Final Fantasy, unfortunately. So we're going to say graph Ford-Fulkerson. We're going to do on graph G, the source will be 0, the destination will be 5, and I'll just create an integer value here, so max flow is equal to 0, and then I'll just pass in a max the reference to that, so we can get the value there. So then we're going to say the string is equal to graph toString, pass in reference to G, and printf percentage %sn, or new line, and print out the string, free the string, and then we'll also print out the maximum flow, and then at the end we can graph free the FF graph. So if I am right, we should just get the original graph. Oh, no, we did something wrong. Great. Segmentation error. Alright, segmentation fault. Path DFS. Alright, perfect. It's not the actual algorithm. Visited at I is equal to false. Why do we get a segmentation fault here? I'm actually confused. We malloc. I mean, maybe if I do a character pointer, that might be a little better. Nope, still same shit. That doesn't make any sense. This is actually confusing now. Maybe if I do 0, but no, that wouldn't fix it. Yep. Path DFS start. Alright, let me debug and break at graph.c325. So I'll run this. Next, print visited. Oh, okay. This just never allocated. But why would it not allocate? Now this is confusing. This has me perplexed. Let me make sure graph copy is working. So I'll just say graph ff graph is equal to graph copy pass in G. Oh, okay. Yeah, this was working. I just passed in G rather than a reference to G. Okay. Alright, now let's run this. God damn it. I did this last time too. Alright, that's wrong. I don't know why, but... I'm an idiot. Didn't even call the algorithm. Yeah, I did this last time too, in the Dijkstra algorithm where when I passed in the graph, I forgot to pass in a pointer and I just passed in the structure, so it took the integer value and the first 4 bytes as the pointer address, which gave it some garbage value. So this needs to be a reference to G for the copy argument. So now if I run this, oh great. Segmentation fault. Graph copy. It did it well here, though. What's the segmentation fault for? Oops. Alright, segmentation fault. 98. God damn, this file's getting too long. Here we go. Ret.adjacency lists at I is equal to dynamic array allocate. Shit. Oh, man. What's the difference between me calling graph copy right here versus me calling graph copy over here? That is the question. Wait a minute. Hold the fucking phone. This should be just the regular G. This should not be a reference because G is already a pointer here. Okay. Alright, but I'm still getting a segmentation fault. But why? Why? Alright. Let's get a quick debug in here. I really wish I could put the debugging thing right on the right here. That'd be very helpful. Alright, so 553. Step into this function. Line 90 next. Print ret.n 6. Good. What? Oh, this isn't in copy anymore. This is in graph DFS. Okay. Alright, let me just make sure that that these graphs are actually getting copied properly. Ooh. Does graph.copy not actually return something? That could be the problem. Aha. Yep. Graph.copy does not return anything. Perfect. Alright, that should do it. Maximum flow 23. That's our graph, and as I said before, this will give us the original graph with all the original capacities. So perfect. Good fucking shit. Yep, dumb mistakes. I always slip up on that. Alright, let me find a better example here. I actually just looked at the first example. Kind of a shitty example, but... what about this one? No, not that. Here we go. So yeah, this, you see the residual graph. Oh, this is a bit of a better example, maybe? Is it? You know, yeah, this is because it doesn't have all the edges as fully filled. So let me try and translate this into the... Alright, so we still have 6 nodes. Alright, so we go 0 to 1 with weight 10. Here they have it represented where it's the current flow / the maximum capacity. But here we're just going to consider the maximum capacity as just the weight, so we only care about the maximum capacity, and we'll subtract from that based on the weight of the, or the maximum flow, or the flow of the current path, of the augmenting path. Alright, so 0 to 1 with weight 10, 0 to 3, wait, yeah, 0 to 3. We can do S is 0, A is 1, B is 2, C is 3, D is 4, T is 5. Alright, so 0 to 1, 0 to 3 with weight 8. 1 to 2 with weight 5. 1 to 2, or 1 to 3 with weight 8, or 2. 2 to 5 with weight 7. 3 to 4 with the weight 10. 4 to 2 with the weight 8. 4 to 5 with weight 10. Alright, so let's run this. Maximum flow is 15. In our graph, the last graph, we have 0 to 1 with weight 10. That doesn't make sense. Zero to 1 should be weight 7. Alright, 0 to 3, weight 2. Let's see. 4. Oh, 4 to 2, did it not subtract properly? Maybe it didn't. Let me try doing it using the adjacency list to see if that makes a difference. Alright, we still got 15, but no. Alright, Alright, so is it not doing this properly? Huh. Alright, you know what, let me debug this. Alright, yep. We should be going 0 to, this first edge should be 0 to 1. Alright, so print ret edge dot v1, print ret edge dot v2, 0 to 1, print ret edge dot weight, 10, print residual edge dot weight, 3. So this should print ret edge dot weight. Or damn it, okay. Print ret dot adjacency lists at I dot list at 0 dot list at 0 dot weight. Damn it. Seven. Am I returning the wrong graph? Oh, you stupid dumbass. I'm printing out the wrong graph. God damn it. Alright. Good shit. There we go. That's what I wanted. Perfect. Alright. God damn it. Wow, I need to clean my shit up. Okay. That went on for 20 minutes too long. We finished writing the code 20 minutes ago and I'm still fucking doing this. Alright, either way. That's Ford-Fulkerson. It's a pretty cool algorithm. I like it. It makes a good amount of sense if you understand what the residual graph really means. And I mean, I can go over that again real quick. So I'll just recap quickly. We have our graph, this thing, the graph, which is here, and our residual graph kind of represents everything that we can undo, or that we can everything that we can do to the graph. So all of our it holds all of our augmenting paths. In terms of where the weights are the remaining capacities. So for example, in the residual graph right here, we see that the path from C to D has a remaining capacity of 2. So that means that we can increment the flow from C to D by a weight of 2. And from D to C, there's a path that has a remaining capacity of weight of weight 8. Remaining capacity of 8. So therefore we can send 8 units along from D to C. But in our original graph, there is no path from D to C. So this is just equivalent to taking back 8 units of flow along the path C to D. So we're undoing 8 units of flow there. I hope that's maybe like the 4th time I've explained it, but I worried that I did not explain it too well. But yeah, anyway, that is Ford-Fulkerson. Next time, I'm not sure what we'll do. We might look at Prim's algorithm. We could do Kruskall's algorithm. There are a few things that we can do, which will be pretty cool. But yeah, I hope you guys enjoyed this. I hope you learned something. And I will see you guys next week. Have a good one.